Okay, this is chapter 17 in the purple book, but that's irrelevant right now. It's the movement into electricity, and I've never shied away from the fact that electricity and magnetism is not my favorite. We are pretty much at the end of the school year if you were watching this when we had to go online, and we only have so many classes left, so we're going to kind of move through this pretty quickly just to kind of get some information and some understanding, hopefully, of why some things happen, like rubbing balloons against your head and what happens with all of that. Okay, so this is just basically a little bit of a setup with obviously what it says here, like static electricity and charge. Some of the real basic stuff, obviously, we already know. Protons positive, electrons negative, that sort of thing. Everybody probably has an idea what static electricity is. Okay, it's a buildup of electric charge. I already mentioned how you can see this kind of happen if you rub a balloon against your head, and then you could kind of put it on the wall and it sticks there. What happens? We'll get into that. You should also know that like charges repel and opposite charges attract. I always make students, or in class I'd have students watch an old Paula Abdul video called Opposites Attract, where she's dancing with a cartoon bunny, which was probably revolutionary in the late 80s. But here's a little something too. If we have two charges, like 2 plus charges, if you take them further apart, obviously I think it just makes sense that the attraction between the two, or even the repulsion, if it's a plus and a minus, the attraction, or if it's 2 pluses or 2 minuses, the repulsion would decrease as the distance increases. Okay, so if you remember too, we had a equation where it was F equals big G m1 m2 divided by r squared. Now this does not involve charge. This would involve like 2 massive objects, like the person and the earth, or the earth and the sun, something like that, and then the force of attraction between the two. But if you remember, as this increases, the distance between the two, this goes down. Same thing with the force, okay? And later, the equation that goes with that. All right, electric charge is never created or destroyed. It's just moved from one place to another, okay? I'm not going to so much get into this, all right? But electric charge is conserved. Get my notes all mixed up here. It's always quantized. I think that's probably obvious when we're talking about plus or minus 1e. Okay, so that would be like a charge, let's just say an electron, right? We can't split it in half. Down here, what happens when you rub a balloon against your head? So, I don't know about you, but whenever I think about when you rub something against something else, okay, I always figure the one that you're rubbing is stripping the electrons off the other. Okay, so for example, the balloon, you rub it against your head, and then the balloon's negative, okay, because it's pulling electrons off. Or you take a cloth and you rub it against some rubber or a glass rod or something. I always think the cloth is negative, but that's not necessarily something that we can just say for sure. So we get into something called the triboelectric effect, okay? So what happens when you rub your hair against the balloon? I think if everybody's done it, then you can see that the hair will stick up after if you bring the balloon close. Why is that? Okay. So down here it's called the triboelectric effect. Tribo meaning to rub. So basically you have to look at both materials, okay? You have to look at both materials and then where they fall on this chart that's going to be shown here. It has nothing to do with the ability to discharge. Okay, so like, what has a better ability to discharge? A metal or a rubber? Metal would have a better ability to discharge because it is a conductor. Okay? That has nothing to do with it. So here's our series. So anything, if you take 2 things in here, and you could get a series that's, way longer than this. This is a short one. But let's just look at rubber. I know it says hard rubber, but who cares? Rubber is towards the negative end. Human hair is positive. So if you rub human hair and rubber together, the human hair will be left positive. The rubber will be left negative. Okay? Let's say we've somehow rubbed cotton and rubber together, the cotton would be positive, the rubber would be negative. But if we rubbed cotton and human hair together, see, the cotton would be negative and the hair would be positive. So it just depends where it falls on here and which one's closer to the positive than the other, or vice versa with the negative. Okay? So in this case, it was true that the human hair was left positive, and you're actually stripping the electrons, pulling the electrons off the human hair, okay? Leaving the human hair negative because it has less negative charge, it has more positive then, and then the rubber would have more negative, okay? So let's get into here, transfer of charge. If you remember from chemistry, mentioned about metals and how they conduct electricity well because they have this free-flowing, the ability to have electrons flowing between the atoms very easily, okay? It's very similar to thermal conductivity. So like in thermal conductivity, metals conduct heat better. Well, they also conduct electricity better. Glass doesn't conduct heat as well, neither does glass for electricity. So it's kind of similar. And here we go. Conductors and conduction. We don't need to get into much into this. You could just look at it. Conductors conduct, insulators don't. One of the cool things, where is it, rubber here, like on a balloon, if you take the balloon and you rub it against your hair, only the part, so here's my balloon, here's your crazy hair, only the part that rubs against it is going to be left negative, since it's like an insulator. That negative charge doesn't really flow freely around the entire thing. Okay, the fact that it's an insulator keeps it in one spot. And you would notice this if you try to like take the balloon and put it against the wall, and you stick it against the wall, and then you let go and it stays there. But if you turn the balloon and do it the other way, it'd fall to the ground. It's pretty slick. Or if you just dropped it on the floor, you might see that it might roll and then stick a certain way. And that was where the charge would be down, and it's kind of attracted to the floor then. Semiconductor, we use semiconductors in electronics. What if we just use conductors? Well, it would just constantly conduct electricity. We'd have no way of really controlling that. Now here comes the transfer of charge. I already mentioned something about that with the balloon and how it's an insulator. This down here is pretty slick. It's called an electroscope. And you've seen these things maybe in science class or whatever. I'm going to draw it over here. So basically, you have this metal rod hanging down, and then you have like two pieces of aluminum, okay? And it's probably being held up by something. So let's say we bring a rod in here that's positive, okay? Who cares how we did that? We rubbed it against something, it's left positive, that's fine, okay? This positive charge, this wires and the aluminum that's hanging off there, this would be neutral, okay? It'd have equal amount of protons and electrons. But when we bring this positive charge, the electrons would be drawn to it. So those electrons would be pulled up, leaving these down here positive. So what happens if this and this are positive? Likes repel. So these would move away from each other, the aluminum. And the aluminum's light enough where it actually you'd be able to see it like separate, and then if you pulled your rod away, it'd come back down. Now let's say the rod touched this. Okay? If the rod actually touched these negatives, right? Because these are electrons. Our protons, positives, aren't going to move. But the electrons can move. They're very small, right? So we touch these together. The electrons are actually pulled into this rod because opposites attract. They're not here anymore. So this is going to be left net positive. So let's say we touch it and then pull our rod away. These would stay pushed apart because this entire thing would have a net positive charge. Excuse me. No, I'm not sick. I was chewing gum earlier and I think it's all stuck in my throat. Okay. And that leads to this, charging by induction. I think it's pretty cool. It's a cool idea to charge something up and leave it that way. So once again, let's say we have a metal rod, okay? And these are positive. Might be hard to see. And we have a like a metal ball here attached to an insulating rod, okay? It's important that's an insulating rod because basically the ground acts like an infinite amount of negative charge, okay? Or positive charge, whatever, okay? So if you have something that has a buildup of electricity like a power line, and you touch the power line and you touch the ground, the electricity is going to flow to the ground, okay? But anyway, here's our setup. Positive charge. What this does, once again, is it pulls the negative charge over here. All right. So the positive charge isn't going to move, but basically what it does is cause this pulling of all the electrons towards this side. Okay. It doesn't mean that there's no positives over here, but the net charge of this side is negative. The net charge would be positive. If we would just pull this rod away and not do anything, it would go right back to just having equal distribution throughout the whole thing. Okay? But now let's say we do something a little bit tricky here. Let's say we take a little wire, okay, and it's touching the ground, literally the earth, and we touch it to this side. This side is net positive, this one's negative. What it's going to do is it's trying to make this neutral. So this positive here is going to pull negative charges from the ground to equal that out, okay? And then you cut the ground out, okay? So what it did was it pulled these negative charges up into this, giving it more than it did before. Then we take the ground away, and then we pull away our positive charge rod. And then this thing's going to be left net negative. Okay, so here, let's try to describe it real quick. Pull the positive, put the positive rod close to it, but not touching. Okay. It will pull the negative charge over here. Hook it up to a wire touching the ground. It'll be positive on the right, pulling negatives in. So now you have extra negatives. Take the rod away, and then the whole thing will be left net negative. It doesn't mean that there's not positive charges, but let's say there's, this is really kind of dumb, 10 positive charges. But now you would have like 15 negative charges. So the entire thing would be left net negative. And that's called charging by induction. Okay. A very similar thing would happen if, let's say, we just took this rod, put it close, and then we just, boom, touched it. Okay? So let's imagine we have positives and negatives throughout this whole thing. We bring a positive rod close, okay? That'll leave it kind of looking like this, all right? Now let's say we touch it. So you actually touch it. These negative charges will want to go into the rod. Then we pull the rod away. This would actually be left net positive because now it would have less negatives. Okay, I'm going to try to do that, hopefully I'll do that in another video in demonstrations, okay? And here it says the ground is an infinite supply of negative charge. So, what happens when you get these charges in proximity or closeness?